If my function is continuous on an interval, then the average value of a function or the mean value of a function is going to be the integral from a to b divided by b minus a, or it's going to be the integral of a function multiplied by 1 over b minus a. And if my function is continuous of the interval, okay, let me come back to this one later. So if my function is continuous, then the average value or the mean value of a function is going to be given by this formula. Geometrically speaking, let me actually kind of do this. When you have a function f, so your function f can actually wiggle a lot. So if you imagine your function f look like that, it just look like, let's say, just look like a water wave. So if you want to find what is the average height of your function, then one way you can do that is you can imagine your function. Like I said, you can view this as being water height, this being like a water wave. If you put this in a container, then it will stabilize. The average value of the function is going to be the average height of your function. It's going to be the depth of the water when your water stabilize. So what essentially happens here is, if you look at the area of this guy, the area of this guy is the integral of a to b of f of x dx. But your water, it doesn't change volume. So this is the same as the area of this guy in the other graphs as well. So the area under your function should remain unchanged. So this area is the same as this area. However, this is a rectangle, and I knew the width, I know the base, this is b minus a, so I can see that this average value of the function is going to be just the area divided by the width, which is going to be 1 over b minus a of the integral from a to b. Yeah, so this is the b minus a. So this thing is the width of your rectangular strip here.
How do we know that they're equal? How do we know that the area and the heat are equal?
Oh, because you mean in principle or in calculation? In principle, let me think. Let me just say this is for analogy. In principle, why do they have to be equal? Let me think. I think that's too hard to say. So let's just say in principle they have to be equal. So that's why this formula works.
How in calculation?
Huh?
How in calculation?
In calculation, so in calculation, so the area, because you can see that the area under the function is going to be the integral. So if the area has to be equal, then even when it changes shape to be the rectangle, then you can find the height of your rectangle too. So if you imagine like this being a water in a container, then this is gonna be your volume of your water. So because when your water stands still, then you can once you know the volume, you know the base of your container, then you can find the height. And this is just so happen to be the height of your water. Okay, yeah.
That's also like in principle, right? Like we have like a water tank.
Right, right.
There's like this amount of water.
Mm-hmm.
So when the water is moving,
Yeah.
it's still the same amount.
Right. So I think it probably would make more sense if you think this as a discrete. So if you imagine each little you can think of it this way as well. If you imagine each of your little if you imagine each of your function value as a height of a person, so this is a discrete analog, so it doesn't really explain the area analog, but I think it probably makes sense. So if you let's say you can also think of the function value as the height of a person. So you want to find the average height. So what you do is you actually have to add all of them and divide by how many people you have. When you add all of them, it's kind of analogous to finding the area. Because when you actually just add just a whole bunch of them and divide by number of students, number of students here is just the length of your interval. So in a way, when you compute the area, compute the average height, you get something that's also analogous to what we have here.
What does analogous mean?
Huh.
What does it mean?
Like you can look up your dictionary. You know what that means. Okay. So now, one thing I have to emphasize, by the way, the average value of a function is not to be confused. I'm not sure if you guys do random variable this semester or next semester. Have you guys do that yet? Okay. So if you want to compute the average value of a random variable, the formula is going to be this guy, where your f, this is the probability density function. So as you can see, there's going to be a little extra x that goes into this formula. So the average value of a function and the average value of a random variable, that goes by a slightly different formula, which is the extra x that you see here. And you also will not have the one overthinking stuff that we have up front. Anywho, let me go back to the example here. I have a rocket and it travels at a speed of this thing 60 squared plus 40 kilometers per second, t seconds after its launch. I'd like to find the average speed of the rocket during its first 5 seconds. So I'm just gonna plug in the formula here. That should be quite straightforward. So that's gonna be, it's the first 5 seconds. So I'm looking for when it goes from 0 to 5. So that's gonna be 1 over 5 minus 0. And let me see. And it's gonna be the integral of f of x. So it's gonna be 6t squared plus 4t dt. So that's going to be 1/5 of the integral. My integral is going to be, let me see, 6t squared. So that's going to be 2t cubed. And 4t becomes 2t squared. And that goes from 0 to 5. I think I choose an easy number just so it's easy to compute. So that's going to be 2 times 5 squared. It's going to be 2 times 5 cubed plus 2 times 5 squared minus 2 times 0 cubed plus 2 times 0 squared. So that's pretty not bad to compute. So that's going to be 1/5 times 250 minus 50. And the other guy is 0. So I end up getting 200 divided by 5. So that's, wait a minute, this should be plus. So I end up getting 300 divided by 5. So I get 60. The unit here is going to be kilometers per second. And just a little, you guys don't have to take physics, but let me just tell you a little physics fact here. When you integrate the speed, you get the distance. In this case, because you integrate the your velocity function, which is 6t squared plus 4t dt, when it goes from 0 to 5, you get what you have in here, you get 300. So this thing actually means that during the first 5 seconds, your rocket travels for 300 kilometers. So when you compute the average speed, you get 300 divided by 5. So that's why you get that the average speed is 60. Because that just means in 5 seconds, your rocket goes for 300 kilometers. In 5 seconds, it goes 300. So that means on average, it goes about 60 kilometers per second. The last thing we have here, this is probably a theorem. I'm not sure why I don't have a name. If my function is continuous from a to b, then the average value of a function is going to equal to f of c for some value c in the ab. So it just means that if my function is continuous, then for some value of a function, for some value of c in the AB, f of c is going to equal to the average value of a function. It just means that at some point in the interval, your function value has to equal to the value of its average.